right? So here, so that is a responsibility of your system call. So here, open system call, already I said, here open system call, the syntax fd equal to open within the argument path name flags and mode I already covered. So here, path name, your path name can be absolute path name, and then a relative path name, and then it requires flags. All right. So you are opening a file for the sake of read, write, or execute. So and then there will be a modes. All right. So this particular modes will assign permissions for three category of users. For owner, three permissions; for group, three permissions; for other category, three permissions. Like this, right? So in order to set permissions for all the three category, so we have a modes, right? So these are the three arguments which are supplied for open system call. So here, whenever it is open, the open system call return as some value. So that value will be stored within a file descriptor. So that particular files descriptor will be made available within the user file descriptor table, within a PCB process control block. You might be studied in your operating system, right? So here, within the PCB, so user file descriptor table will be there, right? So here, the file descriptor, one entry will be assigned, right? So here, from here, here, first 0 1 2, right? Already I said these are the file descriptor values 0 1 and 2, so which is a reserved. So 0 for standard in, 1 for standard out, and then 2 for standard error, 0 for standard input, means whenever your program or your command is taking an input from a keyboard or from a file. uh, Here, we the file standard file descriptor will be 0. All right. So and then coming to the one, whenever your command or your program is producing a result, so it will be returned to your, monitor, so which we call it as a screen, right? So here, the standard file descriptor for standard out is 1, and then when your command is producing a some error, so here, the file descriptor value will be 2 in this case. So it is also going to be returned to your monitor, which we call it as a display unit, right? And then remaining file descriptors, right? So 3 4 5, so like this, so the entries will be assigned for whenever we are opening any file. So within your system call or within your program, it can be a C program or anything. So whenever we opened, if I open only one file, so one file descriptor value will be assigned. If I open another system call, so another file descriptor, so the after 3, 4 will be assigned. If I open another, so after 4 it will be assigned 5. So like this, so the entries will be there within a user file descriptor table whenever I open any file, right? So 3 or 4 or 5, right? So from this file descriptor, there will be a pointer to file structure table. So here, within a structure table, file name followed with whenever it is opened. So whenever it is open, so here the count value will be 1. So and then there will be an inode number for a particular file. So whatever may be the file which I given in the path, right? So that file name, that file inode number, right? So there will be a inode number, and then with the help of this inode number, so there will be a pointer to inode block, inode table. So within inode table, when it goes to the inode table, there will be a data structure about a file inode number, inode number followed with file name, followed with pointer to the data block, what is the size of your file. So all these things will be present within your inode table, right? So here direct one to direct three, direct one, so like this there will be a names, it indicates that. So it indicates that it is pointing to the data block within your disk. All right. So when you go some extent more about the Unix operating system, so there you are going to study more about the inode, right? I mean there you can see one tree structure regarding the direct one, direct two, direct three, direct four, where this pointers will be pointing to your disk block, right? So here just I simply mentioned what is there in inode block. So inode number, so the size of your file, so at the same time pointed to your disk block, right? So like this file structure you need to keep in mind. So whenever we open any file, within your program or within your script, right? So here you can see an example. So here you can see the example. In this particular example, you can identify the user file descriptor table. So here 0 1 2, forget about 0 1 2. So after this 3 4 5, so meaning is there are three statements, right, where three files are opened. I used this open system call three times, means I used the file descriptor, three file descriptors. So file descriptor 3 4 5, all right. So this is a pointer to the file table. So the count is one, means so etc password file, I referring to the etc password file, right? So and then read, so for the reason, for what sake, so I'm opening this particular file, means so o underscore read only, means reading purpose, right? So and then there will be the another file I have opened in a file with the help of file descriptor to open local comma o underscore rdwr, means read write. So read write, all right. So here the count for a particular file local will be only once, right here in a file table. And then we are opening this particular file, read and write. Here you can see in the inode table the count for local file is one, all right. So and then coming to the another statement, fd3 equal to open again, file name is etc passport. So here within a file table, there will be another entry. We are opening this particular file here for the sake of write, for the sake of write. So here this will be pointing to the same inode block. So here you need to remember it will point to the same inode block, means so the count within inode block will be increased, all right. So increased means two times I'm referring to the same, two times I'm referring to the same file, right? So um, this is a case here. This is a structure, right? This is a data structure after open, right? Whenever we open, we can see the relationship between a file descriptor table, file table, and inode table. So this is the thing you need to keep in mind whenever we are opening any file, all right. So here you just see, uh, I have two user file descriptor tables. Meaning is, so this is a user file descriptor table for process A, and then this is a user file descriptor table for process B. Right, within your computer, there is no only a single process will be there. Within your computer, you can see more than one process will be running. Right. So if more than one process will be running, means for every process there will be user file descriptor table, right? So here that process has one or more file descriptor, right? That process will have one or more file descriptors, right? Here the process A has a three file descriptors, process B has a two file descriptors, right? So and then it is pointing to both the process are pointing to the same file table, right? And then here this process are pointing to the inode table, the same inode table. So the inode table means there will be a inode table only one. In that particular inode table there will be a blocks. So each block will refer to one file. Each block will refer to one file. Here one block count is 3. It indicates that so this file is opened. This file is opened 3 times, right? That means within a process A twice, within a process B once, right? So total, so there will be 3 times a particular file is opened, right? So like this, the count within inode table is going to be increased. So this is about user file descriptor table, right? So here this is a data structure you need to keep in mind in every time, right? So if you keep in mind, you can write easily. Exam means the people when the question write a short note on open system call means if you write all this particular, you will get a good marks, right? Full marks, right? If it is a 10 marks, you will get 10 out of 10. So that's what we expect here. All right. So here coming to this another system call, we call it as a read. All right. So here read system call. Already I said read system call for the sake of reading block of a data, right? So when I opened any file, at the same time we are trying to read that particular file from the data block. So from a data block, I need to read some amount of data, right? So here we need to use a read system call. So the syntax is number equal to read. So there are three parameters, FD, buffer, count. You try to remember three parameters are supplied for read system call. One is a FD, means file descriptor already opened. Another one is a buffer. The buffer, the third one is a count. So the first parameter is a FD, is a file descriptor. When a file is already open by open system call, and then there will be a entry within the user file descriptor table. At the same time there will be entry within and the file descriptor table, right? So the second parameter we call it as buffer. So the buffer is a pointer pointing to the memory location where I need to read some amount of data, right? So from my data block, so data blocks are separate, right? So there will be a inode block, there will be a data block. All file data will be stored in data blocks only, right? So um, uh, all the data will be stored within your data blocks only. So here whenever we are expecting to read some amount of some volume of data from the data blocks, so I need from which location I need to read, from which location I need to read. So at the same time from that particular location, how much volume of a data I need to read. So how much volume of a data I need to read means how many bytes I need to read. So this how many bytes I need to read means here I'm specifying a count, right? So the last parameter we call it as a count, right? A count specifies a maximum number of bytes you want to read, right? So this is what we expect from the uh, variable number, right? By using a read system call. So we like to read some volume of a data from the data block by using a read. So by using a open, I already opened, and then by using a read, I'm trying to read some block of a data. Here C syntax, here by default whenever we are using this read system call, so there are something we need to keep in mind. Header files, right? So header files, what mandatory header files to be remembered, to be used, right? So those header files need to be included include and uh, 5C3, 5C5, hmm? Wow, 5C5, mute, right. So here we need to include this particular uni std.h, and then data type size underscore t. This is a data type used to represent the size of a particular block where we need to read or write, right? Whenever I need to read or whenever I need to write any block of a data. So here within the syntax, the data type to be included size underscore t. Read followed with the file descriptor is already an integer value, and then this is a pointer pointing to a memory location, right? Pointing to a particular data block. So here the count is what is a maximum size I need to read, what is a maximum size, right? So size underscore t, maximum size I need to read read from a data block, right? So these are the three parameters we are expecting from the reader, right? So and then write system call, the syntax for write system call, the syntax for write system call is number equal to write, followed with three parameters, fd,
ఇవన్నీ
fd comma buffer comma count, right? So fd comma buffer buffer comma count. So here already I said FD, file descriptor of a file you want to write to it. It normally returned from the open, right? So already the file
లానొద్దులే
రామాంజనేయులు సౌండ్ వస్తుంది B6, right? So buffer, so the second parameter is a pointer pointing to memory location, pointing to the memory location, right? From which point I need to write, right? So data blocks is a separate unit. So within your file system in Linux operating system, so it's not like a Windows, right? If you within a Windows means there will be a folder. So within that particular folder, folder data structure will be there. Within that folder itself, file name will be there. Regular files will be there. Right. So the data about that particular file will be there. Whenever I click that, immediately I can see the content which is present in that particular file. But within the Unix operating system, so when there is a folder which is visible to you, but it has a nothing, right? Only that file name will be there, and then the data regarding that particular file will be present within your data blocks. So it is a separate unit. So within your file system, so within your file system, at the beginning I said, so Unix operating system is going to partition your entire file system into a blocks. So first one we call it as a boot block, a second one we call it as a super block, a third one we call it as an inode block, a fourth one we call it as a data block, right? So here within the data block your data will be stored. So here with the data which is stored in the data blocks, it will be multiples of 512 bytes, multiples of 512 bits or bytes, right? So in that way, the data blocks will hold the data about any file, right? So here the second parameter, the buffer, is pointing to particular data block, so where I need to write, and then a count is a maximum number of bytes I need to write on to that location. So maximum number of bytes I need to write on to that particular location. Here you try to understand. So when here when there is no specified space is available in that particular block, So and then what the write system call will do means, so the write system call has a provision. So the write system call is currently working in the kernel space. That thing we need to keep in mind. So it is working in the kernel space means it is working in the core operating system space. I mean here there will be some algorithms, right? So there will be some procedures, right? So those procedures will take care in order to assign a block dynamically for your uh, for a write system call, right? So when it is expecting a data block, additional data block means, so here it will assign, right? So by using some algorithms like alloc, so it will assign a data block, right? So and then it will make an entry within a inode table. All the things will be taken care by your kernel itself, right? So that's what we need to remember about write system call. So the general syntax, you need to keep in mind size underscore t, a data type write followed with int fd const void star buff, size underscore t the count, right? So buffer is a pointer, star buff indicates that it is a pointer pointing to the data block where from which block I need to start writing, how much volume of a data need to be written. This is what I expect, right? So this is about write system call, right? So and then we have uh, 1 minute. Okay. Coming to another system call, we call it as close. Here, you try to remember whenever here a file descriptor means when a program is currently running, it will be resided within the RAM, right? So here we can say that it is a one process. So within that particular process, so there can be a one or more number of file descriptors will be opened. So one or more file descriptors will be opened, so for some special operations. So here in that particular process, if there is a one file descriptor or two file descriptors which is already opened, so it need to be closed when it is no longer required at the end of your program. So at the end of your program it need to be closed, right? So if I close and then the user file descriptor table, the entry will be, the link will be removed. so that it will be made available for another process, right? So here every process, right, need to do every process it need to do at the end of your program means there must be a close system call, right? So here we need to close a file descriptor which I opened, right? So which I used, the file descriptor which I used for opening, it need to be closed, right? So this can be done by with the help of close the parameter, only parameter close system call will take is file descriptor, FD. FD is a file descriptor for open file, and the kernel does a close operation by manipulating the file descriptor and corresponding file table and inode table entries, right? So here when a close operation is initially initiated, when close operation is initiated, so your kernel will take care, your operating system will take care. So here within the user file descriptor, so there will be a three entries, three tables will be associated for FD. In file descriptor, for file descriptor there will be three tables will be associated. So one is a user file descriptor table, one another one is a file table, another one is an inode table. So from the inode table there will be a data block will be associated. So here main important thing is it need to de-link, it need to de-link within the respective tables. So it need to de-link within the respective tables means whatever may be the entry which is available in the user file descriptor table, so it need to be removed, right? So this will be done by your operating system. So when the close file descriptor close system call will be initiated at the end of your program, right? So here we'll see with an example how it is going to happen. I have an example. I have two figures, right? Figure 5.11, figure 5.4, right? Which is going to illustrate the close here in the there will be a two user file descriptor tables. You can see in that diagram file descriptors 3 and 4 in the user file descriptor table made empty. So the count field of the file table entry is now 0. uh, we'll see with the example, right? So here you can see the table. So user file descriptor table for process A, right? Here file descriptor 3 for FD1, file descriptor 4 for FD2, file descriptor 5 for FD5, right? So these are opened initially. So there will be a pointer within a file table. There will be a pointer within the file table for FD1, FD2, FD3, right? Sorry, FD3, FD4, and FD5 entry in the file table. At the same time, there will be a pointer to the inode table. So this is the case when your program are beginning. Whenever it is executing, right? Whenever it is executing, you can the data structure for a particular process, the data structure for that particular process. You can see the kernel will make the data structure within the user space and the kernel space. So the data structure it will be like this. So and then whenever there is a close file descriptor, so when if I use a close fd1, close fd1, close fd2, close fd3, so and then all these links will be removed, right? I have a user file descriptor table. There you can see 3 and 4 is null, right? So 3 and 4 is null. If I may the fifth one close fd, if I say, so it is also going to be made null, right? So like this this is only the user file descriptor. So then when program is terminated, when a program is terminated, so you can see only the user file descriptor table. So there is no pointer to file table or inode table. This only the table within the user space, within the user space, right? So when another process come into picture, so again there will be entries. So again this data structure will reconstructed. All right. So that is what we can see here, the operation behind all these particular system calls. All right. So another system call, we call it as a creation, file creation. Right. So open system call, already we are familiar. So which is responsible for opening a file. Here the create system call used for creating a file. So if the file is not available, so I need to create a particular file, whatever may be the file name which I mentioned within the path name. So within a path name, whatever may be the file name I mentioned. So with that particular name, whatever may be the path I mentioned in that particular path, so the file will be file will be created, and then what permissions I am expecting for the file which is created means I am going to specify. So for the user what permission, for means for owner what permission, for group what permission, for other category what permission. So all these things we are going to specify, right? So that is these are the two parameters for create, right? So again whenever we are creating, and then the file descriptor will be initiated. So file descriptor fd equal to create path name, followed with modes, right? So followed with modes. So here the path name is a path which indicates a file to be created in that respective path, right? So if it is a relative path, so only file name we are mentioning means it is a current working directory. So if it is an absolute path, it indicates that it will begin from the home directory. So home directory followed with the subdirectory followed with the file name. So like this we have a hierarchy tree, right? In that path the file will be created. So and then modes means here we are specifying. So what are the modes, what permissions we like to have for that particular file, for the owner, for the group, and for other category. Here one thing you need to remember, uh, if no such file previously exists, the kernel creates a new file with the specified name and permission mode. If the file already exists, kernel truncate the file, right? So the last statement you need to remember. So most of the case we are expecting the file is not present, we are trying to create, right? So if the file is existing, and then what the kernel will do is it is going to truncate, it is going to truncate that particular, it is going to add for that particular file. So that is what we expect. So here there is an example for create hash include, we are including the header file stdio.h, systype.h, systat.h, followed with main integer type file descriptor fd equal to create. I mentioned the file name. So I mentioned a data file .c. So this file need to be created in my present working directory. So and then I'm looking for set read permission, set write permissions for the owner, right? Set read permission and write permission, right? So if fd equal to -1, right? So here I think most of the case the file descriptor may not be -1. So always the file descriptor will be a integer value, positive value. So it can be a 0, or it can be a 1, or it can be a 2, or it can be a 3, 4, 5. Most of the case 0, 1 and 2 may not be there. So it can begin with 3, 4, 5, 6, like this. So here if it is a -1, it indicates that so there is a error in opening a particular file, right? So and then else, if that is failed, so come to the else part. So obviously it will fail. Print a data file .c opened file for the sake of read write access. Printf data file .c is currently empty, right? So only simple thing we are trying to do here. So one file we are trying to create, So and then we are assigning a read and write permissions for that particular data file dot c, and then we are making that particular file as an empty. We are not writing anything onto that file, right? So and then we are trying to close that file descriptor. So already the file descriptor which I opened for create. So at the end, so this is a way we need to close that file descriptor, right? Exit. This is about the create system called the simple way, the simple usage, right? So and then another system called, we call it as a lsec. We'll see in the next class. So thank you. Anything, right? Just tell me any queries. Hello, hello.
Attendance, sir.
Okay, attendance, I take an attendance 53 members, right? Thank you.
I came little bit late, sir.
What is your name? 587.
Yes, sir.
Huh?
Yes, sir.
587 1 minute. ఏం పేరు బాబు నీ పేరా?
Khan, sir.
Huh?
Arifullah Khan, sir.
Arifullah Khan. Arifullah Khan. Okay, thank you.